So we can start our session for today. Can you please confirm whether I'm audible?
Audible.
Yeah, thank you. So let me just present my screen. Is my screen visible?
Visible.
Okay, thank you. So I welcome you all for the week 8 and the very last live interaction session for this course, Colloids and Surfaces. This course is offered by Professor Basavraj from the Department of Chemical Engineering, IIT Madras under the NPTEL program. Myself, Pratyumnan, a research scholar at the Department of Chemical Engineering, IIT Guwahati, Assam, conduct the live interaction session for this course every week. So, if you remember, in the last 2 or 3 live interaction sessions, we have discussed more about the concept of electrical double layer. So, we discussed on what is an electrical double layer, what are the different models of the electrical double layer, such as your Helmholtz model, and then the second one was the Goy-Chapman model for electrical double layer, or you can also say it as the diffusive electrical double layer. After which we discussed about the combination of both of them. So let me just go to that last week's presentation. So if you see here, first we discussed about the Helmholtz. So over there, the variation of your potential away from the surface was linear. Then we discussed about the diffusive layer where we incorporated the random thermal motion that the molecules have in their system, inherent thermal motion of the molecules. So over there we describe the variation of the potential away from its surface as exponential. Then the third one we came for was the combination of both. So up to a particular layer, the variation is linear. After that particular distance, the variation is exponential, and we describe the potential at this place, uh, uh, or the region where the potential varies linearly or drops linearly was called as a Stern layer, beyond which it was a diffusive layer. The potential at which there is a transition was called as a zeta potential, and after which we described about the different models. So towards the end of our lecture, we discussed about, yeah, the net interaction. So when you keep two planar surfaces or two bodies which are interacting with each other, there are usually two types of interaction that happens. So one is the electrical double layer interaction. So when you have two planar surfaces, the electrical double layer interacts with each other, or there will be a repulsion. And then there was another type of attractive force that, or another type of interaction is present between the two planar surfaces. So can you tell what is the second one? I mean, it's there in the presentation itself. Yes, any responses? So when you talk about the net interaction energy, you have two. One is because of the interaction between the electrical double layer of the two surfaces. And then the next one is the, what is the next one? So it is the van der Waals forces of attraction. So that is what, those are the two types of interactions together, what you call as a net interaction energy. So these two interactions are usually present between, when you consider the interactions between two planar surfaces, you have these two. One is the van der Waals. Again, I'm repeating, one is the van der Waals forces of attraction, and then the other one is the interaction between the electrical double layer from the planar surfaces. So we discussed, after that we solved this problem and discussed how this net interaction energy is actually going to change with different parameters. So one of the parameters that we took was the variation in the surface potential. So we assumed two different surface potential. One was 100 millivolt and another one was 200 millivolt. So we derived the equation, and when we plotted, yeah, so the first one that you see is for 100 millivolt, and then the second one, the orange color graph is, or the orange color plot is for 20 millivolt. So if you see, as we increase the surface potential, the energy barrier, if you see this point, I hope you are able to see my cursor. Let me just, so this point at 1, so that is the energy barrier. So as you keep increasing the surface potential, or if the surface potential is at a, or if the surface potential is high, then the energy barrier for coagulation is high, which means that the system will remain stable. But if you see, in case of 20 millivolt, that energy barrier for coagulation is lesser. So the system can easily cross this energy barrier and coagulate with each other. So that is something that coagulation is, means that the system is going to get unstable. If your system is going to be stable, which means that there should not be any coagulation. If there is no coagulation, you call that colloidal system to be stable. So for that coagulation to happen, that particular the system has to cross this energy barrier. If the energy barrier is high, which means that the colloidal dispersion is going to be more stable compared to the colloidal dispersion with a lower surface potential. So this is how we, or this is what we saw in the last session on calculation of the, or the way, or on observing how your net interaction energy profile is going to vary with your surface potential. So today we will further discuss on these concepts. So we will be discussing quite a lot of problems today. So here you go. So this we discussed in the last class itself, or like one of the problems. So this was actually given as a kind of, assignment or a home task, whatever you can take it as. So I just want to make sure that this question is also solved. So I have given it again. So the question states that calculate the excess pressure between two planar surfaces. Again, here we are taking planar surfaces, but it could be between two planes or two spheres, or between a plane and a sphere. So depending upon that, the equation will vary. So but here we are asked to calculate the excess pressure between two planar surfaces, and these planar surfaces is separated by a distance of 2 nanometers in 20 mole per meter cube aqueous NaCl solution, which has a surface potential of 60 millivolt at 298 Kelvin. So how do you think we should solve this? Or or any thoughts on solving this? We have discussed this in the last week live interaction session as well. Let me minimize. So any thoughts on how to solve this? Okay, I've given the equation again. So let it be this way. So this is same as the concept of two planar surface interacting with each other. So just give it a try. Let me just wait for a couple of minutes before we solve the problem. But again, please try solving it by yourself, and if in case if you get answer or you're stuck somewhere, please let me know. So any ideas, or because if I'm not wrong, I guess you have a similar questions even in your assignment 7. So let me share the formula, then I hope you will have more. So this is the formula. Fr, the repulsive force, again the repulsive force, and then the excess pressure is equal to the repulsive force. That is equal to this big expressions that you get. So you can use uh, that here as well. So it is 64 times k t n infinity sigma gamma square exponential of minus h by kappa inverse, and then your gamma is nothing but exponential of the Boltzmann factor Ze psi by 2 kbt minus 1. Of course, Boltzmann factor is Ze psi by kBt. So this is that divided by 2. So you have in numerator exponential of z e psi by 2 kBt minus 1 by exponential of z e psi by 2 kBt plus 1. So you are given with NaCl solution. So what will be the value of z? Value of z for, yeah, 1. So, so z, both your plus as well as minus, that is for your both cation as well as anion, it will be 1, or you can say minus 1. So for cation it will be plus 1, Na plus, and for anion it will be minus, Cl minus. And your psi, that is nothing but the surface potential, is given as 60 millivolt. After that you have your kb is the Boltzmann's constant, so that is nothing but 1.38 into 10 to the power let me just zoom this, 10 power minus 23. Units are joule per Kelvin, and temperature is given as 298 Kelvin. So, and you know the value of E is nothing but uh, the charge carried by one electron. So that is 1.6 times 10 to the power minus 19 coulomb. So since you have these values, can you just please calculate and let me know what is the value of gamma? So you need to substitute in this expression. Exponential Z e psi by 2 kBt minus 1 by exponential Z e psi by 2 kBt plus 1. So what is the value of gamma? So let me also just input the, or let me first calculate what is ZE omega by 2 kBt is. So the value will be, value of Z is 1 times your E is 1.6 into 10 to the power minus 19 times omega, that is 60 millivolt. So here you need to convert millivolt in terms of volt. So 60 millivolt is nothing but 60 into 10 to the power minus 3 volt. So this is your Z, the numerator term, ZE omega by 2 kBT. So 2 times of 1.38. You can take the value that is exactly mentioned in the question. So if you see in all your assignment problems, you have the values given. What is the in the useful quantities? You have the values given, like what is E, epsilon, epsilon naught. So you can use those values directly. So Boltzmann's constant, I'm going to take it as 1.38 into 10 to the power minus 23. Because if you see in your assignment, it is given more precisely as 1.3807. So both are, I mean, close and they are fine to use. T is 298. So this, let me just calculate and tell you. So if you have the answer, please let me know. You mean the entire gamma or ZE omega by 2 kBT? Entire gamma. Okay, so let me also calculate, because let's check. So this value, that is your ZE psi by 2 kBT, that value comes around 1.167. So we have to take exponential of this value. 1.167 minus 1 exponential of 1.167 plus 1. If you find any differences, please let me know. Like the way, whatever answers I get, and if you get something else, please let me know. So this value will be 3.212 minus 1 by 3.212 plus 1, nothing but 2.212 by 4.212. So uh, So it's coming around point 7625. So what value did you get? Like, can you please repeat what value you got for gamma? Okay. So what value did you get for this ZE psi by 2 kBT? Okay, so okay, you just directly substituted in the equation. Okay, okay, okay. Let me just check once whether my calculations are right. Yeah, it is. So there is a mistake from my side. So the value is coming as 0.525. So the answer is 0.525. Gamma is 0.525. So then gamma square will be square of 0.525. So gamma square is 0.525 whole square, which is nothing but 0. Yes. No, I tried once again. It came out 0.525 only. Oh, so, or just a second. Let me just check once again. So this is 0.275. So let me just check the gamma value once again. 3.212. Okay. So which is, yeah, it is 0.525. So 0.525 square is 0.275. 0.275625. Let me take it as 0.275. So you now have gamma square. After this, what you have to calculate is kappa inverse. So for that, you need to use this equation. I hope you are able to remember this equation. Kappa square is nothing but E square by epsilon naught kt times sigma zi square ni whole ni of infinity. So since here we have the, what do you say, the concentration in terms of mole per meter cube, to this expression you need to multiply 1000 times Na, that is your Avogadro number. So it will be nothing but 1000 times Avogadro number times your E square, sorry, by epsilon naught kT. So E naught times Kb times T. This times your Zi Ni square. So that is, yeah, Zi square times Ni. So this is the expression, because over there the N is what is nothing but the number of ions per the concentration of the ions per unit volume, but here we have the concentration in terms of mole per meter cube. So for that we need to multiply the 1000 times Na. So let's first calculate this factor, that is your factor inside this sigma sign, and this is nothing but kappa square, not kappa. So what is the value of kappa? Like, have you calculated kappa or kappa inverse? Oh, sorry. So this will be nothing but, this should be Ci. So here is NaCl solution. So 1 square is 1 times the concentration is 20 mole per meter cube. So 20 plus, for anion it is minus 1 whole square times 20, right? So that will be nothing but 20 plus 0.1, sorry, minus 1 whole square is 1, so that again will be 20. So this will be nothing but 40 mole per. So this factor is nothing but 40 mole per meter cube. So this kappa square, then it will be nothing but, so this expression we have a value like here. Oh, okay, sorry, I forgot to mention the dielectric constant is 78.4. So based on this, if you calculate, this expression's value will be You mean the entire one, or it should be somewhere around 5.405 times 10 to the power 15, or yeah, around that range. You're getting 10 power 36. Yeah. So if you calculate like together, uh, that is with your this Zi square times Ci, and the value should be around, like, let me give you the final value. Kappa inverse is around 2.15 nanometers. So if you use this, and then let me just show the other. So then if you have that value as, if that is the if kappa, so once we have calculated this, your FR, or you can say that the excess pressure, we can use this expression 64 kT. Yeah. Times n infinity. I'm going to take here it as n times your gamma. That gamma is nothing but gamma naught, because you're using that psi value as the surface potential value. So gamma square times your exponential of minus h by k inverse, or yeah, kappa. So this is the expression for excess pressure. But here we need to actually change. If you see here, we have n, but what is given to us in the question is C, which is in moles per meter cube already. So we need to do the, so here you can express C times Na, that is your concentration into Avogadro number, will give concentration in terms of mole per meter cube, into Na will give your N, and your K is nothing but Boltzmann's constant. So Boltzmann's constant can also be given as R by Na. So if you use this to equation in the excess pressure, you can get excess pressure as 64 times. Now it will become R times T times gamma square or gamma naught square times your uh, sorry, exponential of minus h by k inverse. So I hope, I mean, do you have any doubts in this of just modifying the equation? Or like how we are writing this or how we are actually changing this, because that n is not explicitly given in the question. The question will always contain your electrolyte solutions, that or the concentration of the ion in terms of mole per meter cube. So for that we need to do this, what do you say, simplification, or just use different terms. So I mean, express n in terms of c to calculate the equations. Yes. Yeah, so that's how, yeah, that's how. So, hmm. So that's how, like, I mean, you need to, what do you say, express that n in terms of concentration, that is your molarity, m, and Na. So if you remember, n is nothing but, so if concentration means, I mean, molarity times Na, but your molarity, the units is moles per liter. So you need to actually get, here it is given in terms of mole per meter cube. So you have to convert that, then it will become 1,000 times. You can write it as molarity or you can write it as C, that times Na. I mean, is that your question or do you have anything? I mean, so it is nothing but it is the bulk concentration of your electrolyte, or you can say concentration of a electrolyte ion at a far away, at a distance far away from the surface, or yeah. So let me just show that. So in the equations, you can take that as the concentration of the electrolyte solution. Whatever that concentration is given, you can take that. Or like, let's say, for example, if you see, so if you see this figure, only, what do you say, n infinity is something of the concentration of the solution that is far away from the surface. So you can take it as like, bulk itself. If you like, I mean, so for example, let's say, or wait a minute. So just a second, I'm opening the Jamboard. So can you see this whiteboard? Yeah, so for example, if you take a surface inside a solution, or it can be any surface, here I'm taking a planar surface. So there will be the concentration, there will be these electrolyte ions, right? So these are ions. So any ions that is present at a far away distance is called as the, you can take it as N infinity. These are N infinity. You can say that N infinity is nothing but bulk concentration. Bulk concentration. So actually it is nothing but concentration of the ion per unit volume at a distance far away from that particle or from that surface. So since that is in, so here since our electrolyte solution, that units are in terms of mole per meter cube or in terms of molarity, so we need to do that, that slight changes in the equation. Yeah. So I hope, now things are clear. Yeah, so actually, when you have a particle in the system, there will be like two types. One will be the concentration near to that particle or near to that surface, and another is the bulk, because over there, the presence of this particle's effect, or the effect that this particle has will not be there. So that particular concentration is called bulk concentration. So yeah, so I hope you are able to get this. What do you call this kind of like changes that we made to the equation. Boltzmann's constant is nothing but universal gas constant by Avogadro number, and this N is nothing but concentration of your ions, or concentration of the electrolyte ions into times Avogadro number. This 1000 will come if your concentration was in terms of mole per liter, but here we have it here in terms of mole per meter cube. So here we just need to substitute, then it will be like you express 64 times, R value is 8.314 times T. So T is nothing but 298 Kelvin times exponential of H is nothing but it is your separation distance. So here it is separated by 2 nanometers. Times gamma square. So here I'll write gamma square was 0.275, right? So you need to now calculate this expression. So what is the value of this expression? So you can write it as 430,625 3065.26 times your exponential of minus 2 by 2.15. So this 2.15 is nothing but it is your K kappa inverse. So kappa inverse is what is kappa inverse? It's 0.394. So what is kappa inverse? So that is the debye length, or you can call the thickness of the double layer, or you can also say it as what do you call screening length. So it has multiple names. 0.394. So if you multiply this, then it comes around uh, 16,991.554. 16,991.654 Pascal. Or you can write it as or 16.991 kilo Pascal. So this is the amount of excess pressure that is present between the two planar surfaces, interacting planar surfaces. So I hope you also got this, all of you got the same value. If not, please let me know so that we can, just cross verify whether our calculations are right. Or if you have any doubts related to this question, then please let me know. Oh, see, that's the thing. If you remember, we forgot to multiply here with C naught or C, the concentration. So that will be again another 20 factor multiply. So again, that is one of the reasons. So here, since you have quite a lot of terms, sometimes there might be, you might miss out certain terms. So please be careful. This will be again multiplied by 20. So this will be again, it will be multiplied by 20. Then the answer will be quite different. It will be 33983.108. 339,831.08 Pascal, or 339.831 kilopascal. So we didn't multiply that 20, which is nothing but your concentration of the electrolyte, or yeah, concentration or the bulk concentration of the electrolyte. So any doubts? So this question is very similar to what we solved in the last class. If you remember, and yes, even it is uploaded in the YouTube also. So here we asked to calculate the electrostatic double layer repulsive forces between two flat, again planar, surfaces in aqueous Mg magnesium sulfate solution. Concentration was given as 10 and at 1 nanometer separation. So similarly, we calculated the value of gamma and kappa inverse or debye length. Then we substituted in this equation and we calculated at the end the uh, repulsive force, and it came around 755.716 kilonewtons. And same question, just for practice purpose. So the excess pressure value is 339.831. So if you have any doubts, please let me know, or we can go for the next question. Or is there any, or are there any different answers you are getting apart from what I have written here? If you have some other different answer, then let me know as well. So any different answers or any confusions, or yes? Okay, no doubts. Okay, okay, fine. So I hope you are able to understand. And with this presentation, I will try to add a few more questions, one or two questions in the same way, so that it will be like a practice. Next. So this is again a very similar type of question. So which actually would like to solve. It just a few changes to how we have previously solved the how we have previously solved calculating the debye length for the electrolyte solution. So in previous cases, if you see, we always give the parameters like the concentration and the other uh, required parameters, and we asked to either compare the debye length or calculate the debye length, and from there we might ask to calculate the surface potential. But here the question is quite slightly different. So let me read out the question. The question states that 500 ml of 0.001 molar NaCl is mixed with 600 ml of 0.01 molar Na2SO4. Now they're asking us to calculate the molarity of NaCl and Na2SO4, that is sodium chloride and sodium sulfate, after mixing. And they are also asking us to calculate the debye length for the mixture or for both the electrolyte solution together, the mixed electrolyte solution. So the first part is kind of like easy, because it's just that you need to calculate the molarity of the NaCl and Na2SO4 after mixing. After that, once you get to know the concentration of that particular NaCl in that mixture and the concentration of Na2SO4 in that mixture, you can easily calculate the debye length. Because once you mix both the salt solution, the concentration of the NaCl and Na2SO4 will change. It will be no longer 0.001 molar for NaCl and 0.01 molar for Na2SO4. It will change because your volume is going to change after mixing. So since the volume is changing, your concentration also will change. So since the concentration is getting changed, your debye length, uh, I mean, uh, since you're mixing, so the debye length will be different. So first we need to calculate, I'm repeating again. We need to calculate what is the concentration or molarity of the NaCl and Na2SO4 after mixing. Then from there, we need to calculate the debye length. So this is something that is quite, a slightly a different model from what we have seen in week 6 and week 7. So how do you go about it? And so first, since you're adding two solutions together, and since it's a salt solution, they won't be reacting with each other, right? Because it's NaCl and Na2SO4. So there is nothing, so both are salt solutions. So there will not be any sort of a reaction happening between these two compounds. So in that case, your total volume, of the solution will be nothing but, so as I said, they are not going to interact with what do you say, react with each other. There will be no changes in the concentration upon mixing. So it will be just like total volume of the solution is equal to volume of NaCl solution plus volume of Na2SO4 solution. So it's just that it's a sum of both. So which means total volume will be nothing but 500 ml, that is from your NaCl, plus 600 ml, which comes from your Na2SO4. So which is nothing but, so total 500 plus 600 is 1100 or 1100 ml. So this is your total volume of the solution. So for this volume, you have to calculate the molarity. So molarity of NaCl after mixing. What will be the molarity of NaCl after mixing? So we know this when you, what do you say, when you mix two solutions, when you have to calculate the concentration after mixing, you can use this dilution formula. Like usually this is used for dilution. I mean M1 V1, so you can conserve the what do you say, number of moles in the solution. M1 V1 equal to M2 V2. Conservation of moles. I hope you are able to remember, because this is something which is, taught even in the higher secondary level. M1 V1 equal to M2 V2. That is, you are going to conserve your moles before the process and after the process. Right? I hope you are able to remember that. Just a second. So here also you can use the same thing. So you can write this is nothing but molarity of, or let me take molarity as M. M of NaCl, molarity of NaCl times volume of NaCl. This is before it is added to that Na2SO4. Is nothing but, it's equal to what will be the molarity of NaCl in that mixture of solutions. So molarity of NaCl after mixing times volume of the entire solution. Because when you consider this in terms of entire solution, over there the molarity of NaCl will be different compared to, because in the previous, if you see before addition, it is only pure NaCl, but after addition, in that total volume of the mixture, Na2SO4 is also present. So the concentration of your NaCl in that entire mixture will be different compared to uh, the concentration in its pure form. But if you calculate the number of moles in both the cases, it will remain the same. So moles will be conserved. So that's what, as I said, the equation is for conservation of moles. So I hope you have no doubts here. If you have doubts, please let me know. Anyone has any doubts in this step? Okay, so your molarity of NaCl, what do you say? Before is nothing but 0.001 times volume of NaCl is 500, and molarity of NaCl after mixing we need to calculate. So I'm going to keep this same. I'm going to keep this as same times volume of your entire solution that we calculated as 1100. So then you can calculate molarity of NaCl after mixing is nothing but 0.001 times 500 by 1100. So what will be the value? 0.001 times 500 divided by 1100. So it comes around 4.5 into 10 to the power minus 4, or you can write it as 0.00045 molar. So this will be the molarity of NaCl after mixing with Na2SO4. Now similarly, can you calculate and let me know what will be the molarity of Na2SO4 after mixing? Same process. Zero point zero zero 0.00545. Yeah. So molarity of Na2SO4 after mixing is nothing but 0.00 or 0.00545 molar. So now you have the molarity of NaCl and Na2SO4. You have to calculate the debye length for this entire mixture. So That mixture has both your NaCl or Na plus and Cl minus and SO4 2 minus ions. So for that mixture, you are supposed to calculate the debye length. So if you see, the factor that is outside of your sigma is going to be the same. This is going to be same, the part before outside your sigma. But then the one that is inside the sigma, Zi square Ni infinity, will change. So how it will change? So again, here your Ni is in terms of, what do you call, is in terms of molarity, that is mole per liter. So your formula will be like kappa square equals 1000 times Na times E square by epsilon naught k t. So this will be the term outside your of that sigma, and inside will be, you can take it as Zi square times mi. That is your molarity. So now you can substitute your molarity in the equation. So if you calculate, let's first calculate the term inside this sigma. So it will be nothing but, first let's calculate for NaCl. So in NaCl you will have both Na plus as well as Cl minus ions. So it will be 1 square, that I am going to keep it as, okay, let me just write that also, that as well. So it will be plus 1 the whole square. So this is for your Na plus ions times the molarity. So that will be nothing but point triple zero or 0.004545 plus minus 1 the whole square. So this is for your Cl minus ions times same concentration, point triple zero 45, because both the Na plus as well as the Cl minus will have the same concentration, because it's only NaCl is nothing but Na plus plus Cl minus. It will dissociate as Na plus Cl minus. So everywhere the stoichiometric coefficient will be 1. So the both the concentration of Na plus as well as Cl minus ions will be the same. This is for your Na plus, NaCl. Now we will write for Na2SO4. So if you see in Na2SO4, let me write this separately. So your Na2SO4, once you put it in water, it will give two Na plus ions plus SO4 2 minus, right? So it will dissociate like this. If is it correct? When you put Na2SO4 salt in aqueous electrolyte or in water, your Na2SO4 is going to split as 2Na plus plus SO4 2 minus ions. Otherwise, the charge will not be balanced. So, if you take, for example, 1 molar Na2SO4, or for every 1 mole of Na2SO4, there will be 2 Na plus ions and 1 SO4 2 minus ions. So, for these kind of compounds, when you write this Zi square, it will be, so Na is 1 plus 1, so that will be 1 square times your Ci. Here your Ci will be not it will be, so for Na2SO4 your Ci came around 0.004545, but for Na plus ions it will be 2 times of 0.00545. Then plus minus 2 whole square times 0.00545. This is for a SO4 2 minus ion because it already has a charge of 2 minus. So, and it is giving only for every 1 mole of Na2SO4 dissociating, it is only giving 1 mole of SO4 2 minus. So, it is just minus 2 whole square times 1 times 0.00545. But in case of your Na plus, for every Na2SO4 it is going to dissociate, there are 2 Na plus ions getting generated. So that is the reason here you have to multiply this expression with 2. Let me highlight this one. So my advice is please be careful while writing this, because there are a lot of chances that we might miss this concept and just solve it like how we solve for NaCl, where you just write 1 square times 0.00545 for Na2SO4 also. So please keep this in mind while solving your problems. So if you are getting confused with a particular compound, or if, let's say for example, if it is given an asymmetric electrolyte with Z plus and Z minus as 3:2. So over there the cation is going to have 3 charges and anion is going to have 2 charges. Or cation is having plus 3 and anion is having minus 2. So over there you don't need to multiply any uh, over there you don't need to multiply this 2, because over there that salt is going to dissociate as plus 3 cation and minus 2 anion. But in this cases where so in these kind of cases it will be different. So please be careful about this. If you have any doubts, please let me know. So whenever you are given a salt like Na2SO4, or you can take for example AlCl3. So if you take aluminium chloride AlCl3, if you dissolve it in water, it will dissociate as Al3 plus plus 3Cl minus. So over there for every 1 AlCl3 or 1 molecule of AlCl3 or 1 mole of AlCl3 getting dissociated, you're going to get 3Cl minus ions. So so over there you need to multiply that particular, what do you say, that Zi square times Ci times that 3 will be also there, because that concentration will be 3 times of what you have calculated for AlCl3, or what is given for AlCl3. So let me write that expression also here. I hope you're able to understand. If you have any doubts, please let me know. So it will be nothing but Al plus 3 plus, oh sorry, Cl minus, or you can write 3 Cl minus ions. Because here the Cl minus, here the chloride ions has only one negative charge. It has a charge of -1. But to satisfy the valency, it requires 3. So that is the reason it is 3 Cl minus. So I mean, if you have doubts, please let me know. Any doubts related to this? Actually, this is why this question was actually taken up. One thing is, it is different from what we have solved previously, and another reason is, you majority of the time we tend to make this mistake of not multiplying them with their stoichiometric coefficients. So if you see here, this 1 square and this is also 1, so it will be just 2 times of point triple zero 45 plus, this will be totally 1 square, so 1 times 2. This will be minus 2 the whole square, that will be 4. So 2 plus 4 is 6. 6 times 0.00545. So what is the value? Is it 0.0336? Just a second, let me calculate. Yeah, it is 0.0336. So again, so now we have calculated this Zi square times Mi. So if you know this, the value of this expression, if you calculate, it will be around, so now the kappa square will be nothing but 5.405 times 10 power 18 times 0.0336. So the useful quantities remain same. So let me mention that the dielectric constant here is 78.4. Of course, these terms I have calculated before. So please check, verify, and let me know the answer. I'll calculate in my personal calculator and 405 times 10 power 18. It comes around 1.816 times 10 to the power 17 meter power minus 2. So your kappa value or debye Huckel parameter, that value will be square root of this. So that is nothing but 4.26 times 10 power 8 meter. What is the units of kappa meter? Inverse. So if this is kappa, then kappa inverse or your debye length, or what is that is what is asked in our question, is nothing but 1 by this value. So what is the value? It is somewhere around 2.346 times 10 to the power minus 9 meters. So that will be 2.346 nanometers. So this is your debye length for the solution. So if you can take this as an exercise, what you can do is you can calculate the debye length for this pure solutions, that is your 500 ml of NaCl of zero point 0.1 molar NaCl. You calculate the debye length for this and calculate the debye length for this particular as two separate two separate problem, and then compare that with this value and check how mixing two different salt solution affect your debye length. So that will be something interesting to observe. What will be the, or how will this debye length change when you mix solutions, or when mix two salt solutions. I hope the answer is fine. If you have any other answers. Okay, okay. So I received from one participant that the answer is 2.346. I hope everybody's. So since we are running short of time, I'll just read out this question. You guys can take this as an home task or a assignment and solve it and let me know the answer in the next live interaction session. That is your nothing but your summary session scheduled for tomorrow. So the question goes off like something like this. The electrophoretic mobility of a 1 micrometer diameter spherical particle is calculated to be 4 times of 10 power minus 8 meter square per volt second, and this is happening in an aqueous 1:1, that is symmetric electrolyte medium, with a concentration of 50 mole per meter cube at 298 Kelvin. The dielectric constant of the medium is 78.5 and viscosity is given as 0.001 Pascal second. We are asked to calculate the debye parameter and the zeta potential. So the debye parameter is nothing but it is your value of kappa, right? So kappa square can be calculated using this formula, that is nothing but E square, your electronic charge square by epsilon naught K, that is your Boltzmann's constant times T, the whole multiplied by summation of Zi square times Ni infinity. So you have to calculate the value of kappa. Once you calculate this value of kappa square, and then from there if you get the value of kappa, you need to multiply that with the rs. So here rs is nothing but the radius of your spherical particle which you are taking under consideration. So once you get the product of krs, depending upon the value of krs, you have to use the respective equation. So if you see here, I have previously written this condition. If your value of krs is going to be less than 0.1, then you are supposed to use the Huckel equation, that is here, which is nothing but U by E, that is your electrophoretic mobility, is equal to 2 times of epsilon, that is your dielectric constant, epsilon naught, which is nothing but the permittivity of free space, times the your zeta potential, divided by 3 times eta, that is the viscosity of the electrolyte medium that you are taking. Suppose, so this Huckel's equation is valid for dilute solution where the concentration of the electrolyte that you are going to take is very low. Suppose if the value of KRS comes out greater than 100, then you cannot use this Huckel equation in this case. You're supposed to use the Small-Chomsky's equation, which is nothing but U by E equals epsilon naught times zeta potential by eta, which is the viscosity. So this equation, the Small-Chomsky's equation, is valid for high concentration electrolyte solution. And if you see the difference between both the Huckel and the Small-Chomsky's equation, it is nothing but it just differs by a factor of 2 by 3. So here in case of the electrophoretic mobility, your U is nothing but the velocity of the ions and E is the electric field that is applied. So once you calculate the value of kappa and then by calculating the product of kappa times Rs, you will be able to calculate what is the zeta potential. So your dielectric constant is already given as 78.5. Viscosity is already given. And U by E, that is nothing but your electrophoretic mobility. So I like to emphasize here that electrophoretic mobility is nothing but is a ratio of the velocity of the ions divided by, velocity of the ions to the electric field, which is also given as 4 into 10 power minus 8 meter square per whole second. So once you get to know which equation satisfies for the following question or for the following case, you can easily calculate the zeta potential. So that's the reason I am going to ask this, leave it here so that you guys can solve and come with the answer in the next session. So that's all for today. Let me just, yeah, 3 questions what we have done, or do you have any doubts? Let me just stop presenting. So any doubts? Okay. So, okay, so our next live interaction session will be tomorrow from 6 p.m. to 8 p.m. It's actually a summary session. So, where we will, you know, take up whatever doubts you have from week 1 to week 8, and then we will try to solve some of the problems, like including this. Actually, we planned for totally 6 problems, but we were able to only come up to 3. So, in the next tomorrow session, we will take up with this third problem what we have solved, as well as finish off the other 3 problems and discuss few problems for, you know, your sorry, few problems from week 1 to week 8. Any kind of problems. If you have any doubts, please bring it here. We will try solving them. So if you have no doubts, then I think I can conclude the session for today. So this video recording will be available to you soon by this week before your exams, and I'll upload the presentation as well. My email ID will be there in the presentation. If you have any doubts, you're always welcome to email me. So okay, let me just conclude the session for the day. I thank everyone for joining today's session from 5 p.m. to 7 p.m. Our next live interaction and the very last summary session for this course will be tomorrow between 6 p.m. to 8 p.m. I hope to see you all there. We will be solving problems, continuing with the problems what we have for today, and more problems. If you have any doubts, please bring it up so that we can solve. So I thank both Professor Basavraj as well as the NPTEL team for providing me this opportunity to interact with you all this Sunday afternoon. So till the next class, bye and take care.